Hey everybody. Today we're talking about the exponential distribution, which models waiting times between events that occur randomly and independently, basically events that occur according to a Poisson process. Some examples would be times between calls to a pizza place or times between defective products in a factory. The PDF of a random variable with an exponential distribution has the shape of a downward sloping exponential function. I don't think that's surprising given the name of the distribution. In a Poisson process with parameter lambda, so average number of occurrences in a unit interval, the probability of zero occurrences in time x is e to the negative lambda x. If we view x as the random variable, we can compute the probability that x is less than or equal to any specified value x by taking the complement of the event that there are zero occurrences in that time frame. This gives us the CDF of a random variable with an exponential distribution, 1 minus e to the negative lambda x, and of course x can't be negative. Typically though, we write that CDF in terms of theta, which is 1 over lambda, rather than lambda itself. Theta is sort of letting you know about the rate at which things occur. It's the average time between occurrences. We use theta rather than lambda because we're talking about time rather than number of occurrences, so that parameter makes sense. It's also logical because we're now talking about a continuous random variable rather than a discrete one, so it's nice that the parameter feels continuous rather than discrete as well. If we take the derivative of that CDF, we get the PDF. It's 1 over theta e to the negative 1 over theta times x, where, again, x can't be negative. Still, though, it's easier to compute probabilities using the CDF rather than the PDF. And the reason is that if we use the PDF, we have to do a new integral every single time, whereas the CDF sort of has that already evaluated. The probability that x is between a and b is big F of b minus big F of a, and that works out to be e to the negative a over theta minus e to the negative b over theta. Let's do an example. During lunchtime, customers arrive at a restaurant at an average rate of 3 every 10 minutes. What's the probability that less than 2 minutes elapse between successive customers? Between 5 and 8 minutes? More than 10 minutes? Assume arrivals are random and independent of one another. So, of course, we're in an exponential distribution here. We're modeling waiting time between occurrences in a Poisson process. The parameter is going to be theta equals 10/3, the rate at which these are occurring. And so the CDF of this random variable is going to be 1 minus e to the negative 3/10 x. And we're going to use that to compute all three of our probabilities here. To start, the probability that x is less than 2 is just big F of 2. We plug in 2, do some simplification, and we get about 45.1%. Similarly, the probability that the waiting time is between 5 and 8 is big F of 8 minus big F of 5. We plug in, we simplify, we get about 13.2%. Finally, the probability that x is greater than 10 is 1 minus big F of 10, e to the negative third, about 5%. The moment generating function of a random variable that has an exponential distribution can be computed directly from the definition using a definite integral. I won't go into any of the details of that integral. It is an improper one, so technically it takes a little bit of work. When you get to the end, you get a moment generating function of 1 over 1 minus theta t. And as required for a moment generating function that is defined and differentiable in a neighborhood of 0. It's defined for t less than 1 over theta. So we use the moment generating function to find the expected value and variance of a random variable with an exponential distribution. We do that by taking a couple of derivatives of the moment generating function, plugging in 0. These give us the first 2 moments of such a random variable. So the expected value of x, in other words mu, is theta, and the expected value of x squared is 2 theta squared. We can then find the variance of this random variable by doing the expected value of x squared minus the expected value of x quantity squared. Overall, we get theta squared. So the mean and the standard deviation of such a random variable are both equal to theta, to the rate parameter. One more example. Find the median, m, of a random variable that has an exponential distribution. So I recommend pausing the video here, trying this on your own before seeing my solution. we need to find the value m such that big F of m is equal to 0.5 in such an exponential distribution. So we're solving 1 minus e to the negative m over theta equals 0.5. We isolate the exponential, take a natural log, solve for m. Overall, we get a median of theta times the natural log of 2. Remember, the expected value of this distribution is just theta. Natural log of 2 is less than 1, so that means theta ln 2 is less than theta. So the median of an exponentially distributed random variable is less than the mean. And that makes sense since this distribution is skewed to the right.